Okay, I think we'll get started. So today we're going to pick up again with momentum. And we learned last time that momentum is conserved in a system unless acted upon by a force. So let's see that version where it is acted on by a force. And we'll take a particular case of a force that occurs very rapidly. So it's on for a short duration and then off again. And that's called an impulse. And this will be nice for collisions and other interactions that take place on a very rapid time scale. So if we go back to Newton's law here, F equals ma, let's plot force as a function of time. And we have some kind of an interaction, maybe, for example, a hammer coming down and hitting a ball or something like that, or kicking a ball, something like that. And the force then has this time profile where it's off most of the time except for a short duration here over which it's on. Now, to treat it carefully, we need to do some calculus and integrate the area under the curve, and we call that area the impulse. And this is given the symbol J, and it would be Newtons times time. Now, we can approximate this by making a rectangle of the same area and calling the force the average force. So we imagine an average constant force that gets turned on and turned off. Turned on at T1, turned on, or T initial, turned off at T final. Okay. Well, let's take a little, we need to do just a little bit of calculus here. If you haven't had it, just kind of pop out at the end. If you have had it, just try to follow along here. So we're going to figure out J here, and we're going to integrate from time equals 0 to time final the force. And so let's write that using Newton's laws, F equals ma. Well, then A is the velocity, is the derivative of the velocity. A is the acceleration. And so we can change this integral into an integral over velocity, and we're integrating then not from T1 but from V1 up to V final of the mass times the velocity. So mass is a constant that can get pulled out of this integral, and we're left with mass velocity final minus mass velocity initial, and that gives us P final minus P initial, or delta P. So we have two formula now for the impulse. All right, let's work a couple of problems. Let's work a one-dimensional problem here where a mass is coming in and is going to hit a wall and bounce off the wall. We'll say that bounces off. There's no exchange of energy with the wall. It just comes off with the same kinetic energy that it comes in with. So we'll be coming in at 100 meters per second, and we'll be going out at 100 meters per second. Let's just say the mass is a gram. And let's say the total interaction time is very brief, 1 times 10 to the minus 4 seconds. So let's calculate the average force. All right? Well, let's do it with momentum. So let's figure out the change in momentum. A force acted, so it changed the momentum. Had a momentum before the interaction, had a momentum after the interaction. So we can just take the difference, and that will be the impulse. So the final mass is going this way, so positive 100 meters per second. Here's the 1 gram. The initial mass is going in at minus 100, so it's minus a minus, and so we get 0.1 plus 0.1 equals 0.2 kilogram meter per second. All right, well, delta P is delta J, but delta J is the average force times the time. And we know the time of interaction. We know the delta P, so we can solve for the average force, and we get 2,000 newtons in this case. So these impulses are high force usually over a very short duration of time. Let's make the problem a little more complicated and go two-dimensional. Now we're going to have the same kind of collision, so just in and out, same velocity in and out, but we're going to collide against this wall. As we travel, our x direction is going to be obstructed by the wall and will be sent back the other way, but our y direction will continue straight down. So let's calculate each of the individual components. We need to take our incoming speed times the cosine of the angle, and we get this value. It's negative. And likewise, since we're going down as well, we take sine of the angle to give us our y component. That's our initial. Our final component is coming out at, again, a 30-degree angle, but now we're going in this direction. So we end up with positive, but the same value. Now notice the y value is exactly the same because after the deflection, we're still heading downward. So our total change in momentum will be this, and then our y components will cancel. Right? This is the change, final minus initial. And so our change in momentum is directed completely in the x direction. Let's think just of the magnitude, and then we'll remember that our force must then be applied just in the x direction. So we've got magnitude being just this value, and this will have the same time of interaction we had in the previous problem. So we have a little bit less force here is needed because we're getting kind of that deflecting blow rather than head-on blow. And so we get 1,130 newtons. Now, the direction of that, if we were to draw a free body diagram during the impact, the direction is straight that way, so positive. All right, so this is the idea of impulse and how that changes the momentum of an object. We will use this considerably when we talk about collisions. So we will apply this in collision problems, and then we also apply the idea of conservation of momentum. So if we have two objects and they collide, their individual momentum will change, but the overall total momentum won't change.